1915, a giant tank was built to store molasses in Boston's North End. Why did they need to store so much molasses? Well, this was during World War I, when the industrial alcohol that molasses could be distilled into was in very high demand for use in munitions and explosives. On January 15th, 1919, the tank burst. More than 2 million gallons of molasses poured into the streets like a tsunami, crushing buildings and trapping people under rubble as the wave reached speeds up to 35 miles per hour. 21 people were killed and 150 were injured during the event. You may have heard the expression slow as molasses in January to refer to something moving very slowly. So it raises the question of why literal molasses in January would become such an incredible force of destruction. This is what I and many others have found so interesting about the Great Molasses Flood. The tank measured 50 feet tall and 90 feet in diameter. Unfortunately, the steel walls were too thin to support the weight of the full tank. Increased pressure due to fermentation from a recent shipment of warm molasses and brittle steel due to low temperature meant the tank was pushed to its limit. The 40-degree weather also meant the viscosity of molasses would be very high. You can see here the difference between room temperature and cooled molasses. This begs the question, is the 35 miles per hour realistic? To test this, I will be doing a very simplified calculation using the momentum equation. We can make a few assumptions to simplify the problem. Assume the flow is only in the horizontal direction. Any flow in the z or theta direction would be incredibly small comparatively. Assume that the radial velocity only changes as the radial distance changes. Assume the period of time in question, less than a minute after rupture, the radial velocity does not vary with time. Assume that the pressure could be described by this equation, where h, the height of the fluid, is a function of r, and assume that there is no gravitational force in the radial direction. Because there are not many resources specifically on the viscosity of molasses at 4.4 degrees Celsius, I'll be using the results shown in a frame of a video by Nicole Sharp on this very subject. The viscosity is for 0.9 degrees Celsius, which is much lower than the temperature in question, but it provides a good conservative estimation. The density of molasses is about 1,400 kilograms per meter cubed, and the characteristic velocity and length scale are taken from a textbook question on the molasses flood. Now, it's important to acknowledge here that this is a bit of circular reasoning because I'm using the observed behavior of the flood to estimate whether the observed behavior is reasonable. However, this approach should be okay, as if the flow behaves as observed, it would have a high enough Reynolds number that it would be appropriate to neglect viscous effects. If I were looking for the Reynolds number of molasses flowing in a kitchen, for example, you would get a value smaller than 1, and viscous effects could not be neglected in that case. Our simplified momentum equation results in these terms, which we can do some math to and set it equal to radial velocity. We find a constant based on the initial conditions of the tank, knowing that the velocity equals 0 at the start when h is at its initial height of 14.9 meters. I plugged in that constant and modeled the radial velocity based on the changes in height. I would want to see the velocity based on radial distance, but I don't know the relationship between h and r exactly. Since we're just looking for the magnitude of velocity that it can have, only the range of h is really important. The maximum velocity is about 38 miles per hour, a bit higher than the reported value, which makes sense as the velocity would decrease to around here after a few seconds. Now, this is a very simplified order of magnitude calculation that shows that it does make sense for the molasses to have flowed at such a fast rate despite being a high viscosity liquid. The potential energy stored by the tank was incredibly high, impacted by the height of the tank and the high density of molasses. Once the tank ruptured, all of that energy converted into kinetic energy, resulting in a high velocity that negated viscous effects in the flow. A better model could be achieved by utilizing the equations that model gravity currents when a dense fluid, molasses, comes into contact with a less dense fluid, air, and spreads through it. Another example of this is when I open the window to my dorm after Columbia has heated it to 5 million degrees. Consider this case on a non-windy day. The hot air inside my room is less dense than the cold air outside my room, and when I open the window, the cold air rushes inside, knocking over the cups on my windowsill and slamming my door into the door frame. Avalanches and lava flows are also examples of gravity currents. These models are beyond the scope of the current class, but they would provide a better understanding of the molasses flow during the flood.